Hello, um, welcome to another problem session. Today we are going to do a problem in entropy and discuss something about entropy and second law of thermodynamics. These are a couple of problems that illustrate how you can compute entropy. Okay, now this idea of entropy is presented usually in a very mysterious way. We're not going to go there. You probably are familiar with this idea that entropy is a measure of disorder. The more disorderly an object is or a system is, the higher the entropy, right? But that doesn't really help us calculate things. It's also, although it's good conceptual thinking, but not easy to calculate using those kinds of ideas. Entropy is also a statistical property, like temperature is a statistical property. You really need large number of particles in your system for it to have a meaning. So we're not going to go there. If you do statistical mechanics, you're going to encounter entropy in that context. So we are on thermodynamics, so we're going to do in a different way. Okay, so here I'm going to define entropy first, right? Because we're going to calculate entropy, so we should know what the definition of entropy is. So definition of entropy has to do with the idea that entropy is a state property, like energy, like volume, like number of particles. Okay, so entropy. The first thing to do is entropy is a state particle. So some kind of review. Entropy is a state particle, a state property. Entropy is a state property. Something called state variable. Kind of like energy, and you can say internal energy here, volume, number of particles. Then you can list that as a entropy. So number two, entropy, because it's state variable, we define it using an infinitesimal process. So defined using an infinitesimal process. Usually what is called reversible process. Okay, and you'll see, I mean, it's kind of a reversible process, infinitesimal process. The way entropy is defined is a circular thing. Like if it's reversible, then it's like that, and if it's like that, then it's reversible. So it's kind of like a circular logic, we'll see. So here is a definition of entropy. So say you have a P and a V, and you're here, and so you have a P, V, and you go to another point, which is, let's call it P plus dP, and this dP is less than 0 in this diagram, and this V plus dV. So this will be an infinitesimal process. So an example in terms of, and you know from calculus, this dP, dV, etc. can be as small as you like, other than 0, right? So if you say this process involved, this process is a system. I have my system S, and there's an environment, and there's some kind of this amount of heat that it exchanged in this process. Okay, so I'm using a delta here, just say a small amount of heat. So we will call it, this happened because this is a process that we can display it on a diagram. We call this kind of thing as reversible. We just label it like that. Doesn't mean much other than what we just said. So ds for this process will be defined in like almost 3 equals, we just call it 1 equal, its definition. So how much heat that went into the system or out of the system, just exchange in or out. So delta Q, and I have to imagine, if the process is not reversible, then I have to imagine change had to be reversible for it to be definable. And you can see PV corresponds to, in this, if this is ideal gas, you can attach a temperature to it, and temperature, but this temperature is in degree Kelvin. Okay, so this is the definition, and if the process is not reversible, then I can't define it. Okay, so that's the definition we're going to use. Okay, so for a large change, so if I go from, say, some here to somewhere here, so say this is initial and this is the final, then I need to have this thing as a integral over some path it took, right? So maybe it took this path. So on that path, there was the infinitesimal was like that, and every infinitesimal was like that. So delta S, which will S at the final place minus S at the initial place, is just the integral of this thing over T. Okay, and this is a conceptual integral, right? Conceptual. I can't do this integral because there's no variable here. That depends on how I write this. So if you remember, this delta Q can be written in various ways. So if it can be m c dt. So this is like at constant volume. So if this process was like this kind of process, you have a P and V. If the process is like that, so I didn't change the volume. So if this was initial and this is the final, so inference process is constant volume, then it will be like this. Otherwise, it will be like a du plus pdv. Otherwise, right? So if and this will come from dq is equal to du plus pdv, and this is the first law. So you can have this guy can be written as in terms of dt, and this can be written dt if ideal gas. So there are various ways that you can do this, and then this will become a, using this kind of stuff, it will become a regular integral. And that's what we're going to do illustrating these examples. So what's the second law come in terms of entropy? The second law says that when we have this interaction, say interaction leads to heat going in, that means the temperature here, T of the environment and T of the system, is such that naturally if this is happening, then this is bigger than that. So T is bigger than that. And so when you use this thing for the calculating what happened to the environment, what happened to the system. So what you find is delta S net, which is delta S of the system plus delta S of the environment. One will be positive if this heat is going in there. This will be positive and this will be negative. But this will always be greater than equal to 0. It will be 0 if both are, if the process is reversible. So we define it's reversible if it's 0. So we call those processes. So this is equal, if it's a 0, then we call that process reversible. So whatever the way heat went in, if that happens to be, that means delta S environment is a completely minus of delta S of this. If not equal to 0, which will be greater than 0, is strictly greater than 0. So if it's strictly greater than 0, then call that process irreversible. So you will see that this an example of that is problem 2. All right, so I'm gonna with that much review, let's try to calculate answers to problems 1 and 2. Okay, so to do 1, it's probably straightforward. You can see that the temperature of water has gone from here to there, and we can imagine a reversible process. Whether it's done, no matter how it's done, let's call this temperature, and let's call this pressure. So it's done, say, at constant pressure. It was, temperature was here, and then it became over here. So it's done at a constant pressure. So maybe we can say this is the reversible process. So this is not given here how it was done, but I can imagine a continuous process like that, continuous path from some initial to the final on a state diagram. If I can imagine, then I can always imagine infinitesimal. So in this infinitesimal, the formula of delta Q will simply be m c dt, and c will be this particular c, which is usually a constant pressure. So some constant pressure. Okay, so ds is very easy for this, m c dt, and this is T in Kelvin. Okay. Well, so delta S will be just integrate this thing, integrate, and so now the integration variable is T, so this is Ti to Tf, and this thing will come out because not independent of temperature, this thing is constant. So this is just mc log T final in Kelvin, T initial in Kelvin, right? Okay, putting in the numbers, let's see what we get. So we get 100 grams, and this is gram per gram, so I can just 4.186, and then I get a log, and I get 67 plus 273. I forget the decimals over there, and 27 plus 273. Okay, so when we work it out, and the whole thing the units will become joule per Kelvin, right? Because this was joule per degree Celsius. Per degree Celsius is same as per degree Kelvin, per degree Kelvin, because this change in temperature is the same in the two. Let me set up, get the number. So this would be 100 times. Why do 100 times? So 418.6, and I need a natural log, and so this will be 67 plus 273, which I should have added, and that's 300, and it's 52.4. So we get 52.4 joule per Kelvin. Okay, so that's this answer for this is 52.4 joule per Kelvin. Okay, I think that's correct. Let's do 2 now, and it's a interesting thing that 2 is. Okay, in the 2 we have some water, and then at 27 degrees Celsius, and then we plunk some copper, and that one was at 97, I guess 97 degrees Celsius. Then the water initially is that, but then it will go to everything at the same temperature, final temperature. So the water is going to final temperature, and this is going to the final temperature. So here you remember from calorimetry, right, that the energy transferred out of copper will become the energy gained by water, and then equation has to be written down as MH2O CH2O times T final is greater than 27. So this is the energy gained from water, will be energy lost by the copper block times and 97 minus TF. There's a often there's a mistake I find here. Very careful, make sure that this is plus and this is also plus, because TF is greater than 27, that makes it plus, and TF is less than 97, that makes it a plus. Okay, so that's correct. So now I need to solve for TF. Okay, so I went ahead and actually solved this. This was for 100, and this is 500, and this is 4.186, and this 0.385, and this when you solve for TF, you get 49.1 degrees Celsius. Just make sure I got 49.1 degrees Celsius. That's correct. Okay, so now we have to find delta S H2O and delta S copper. Well, for H2O, we imagine we had initial and then final. So this was at 27 degrees Celsius, and this one is 49.1 degrees Celsius. And we imagine it was, I think it was at constant pressure. So we just went from here to here. We can imagine a continuous process. So this is this is not how the original process may have gone, but imagine a continuous process for calculating delta S, okay? Because for this we need reversible. And so when you do that, you can write delta S ds on this process. It just will give mc dt. And so it's the same as what we did over here. So this will simply be mc log T final over T initial, and this has to be in Kelvin. Often that's the problem that people work out. So this is 100 times 4.186 times log, and you have 49.1 plus 273, and then you have a 27 plus 273. So that's going to be one number. And this, for this, we have to also imagine a process. So it used to be here, it went out 97 and 49.1. And so we imagine a process went like that. And ds is same kind of formula, mc dt. And so the answer will be same kind of stuff. When you integrate it, it's going to be same kind of formula like that. And it's going to be 500 times 0.385 times log. Final will be the same way, 49.1 plus 273. Initial is the difference, 97 plus 273. So this is going to be negative and this is going to be positive. So I've gone ahead and done the calculation for interest of time. So for the water gas, 29.75. So this is 29.75 joule per degree Kelvin. And this is minus, I think 26 something, 26.7 minus 26.7. If we're going to have two decimal places, let's keep two decimal. 26.69. 69 joule per Kelvin. Now you can see that over in the real line, delta S net is actually, when I add this up, is going to be positive 29.75 minus 26.69, and then when you add it, 603 joule per Kelvin. So this positive. So this process that happened, this is an irreversible process. But to compute ds, we had to imagine some reversible processes, okay? Because if you state, no matter what kind of reversible process is imagined, we are going to get exactly same value, because it's only going to be depending on initial and final. The change will only depend on initial and final. And this is a very common problem that gets asked when you are faced with a entropy problem. Okay, well, just a reminder, if you haven't subscribed, please subscribe. And if you like this kind of video, make sure you hit the like button. You want to check out my website for more information. I think this is all. I'll see you in another video. Bye.